The periodic function is a function that repeats at regular intervals. The function's period, which we call p, is the length of the interval of repetition. This period is often measured in time, but could be distance or any other unit. So let's take a look at that. If I look at this graph here, you can see that this is repeating, and the repetition is a time period or a horizontal distance of p, period. And so if I start at j and go 1 period, I'm at a corresponding point on the next cycle. If I start at k, I'm at a corresponding point on the next cycle. If I start at m, any point, even a point that's not labeled here, is going to bring me to the same point on the next cycle. So as long as I can say that one cycle copies to the next cycle, copies to the next cycle, and so on, we call this function periodic. An example is a mass on a spring. When it vibrates, it follows the periodic function sine of t. So in order to model different springs moving at different speeds and heights and so forth, we would use transformations of the sine function in order to do that. We can look at a few examples of periodic functions. Temperatures over the course of a year are generally periodic, and this graph that you see here is the normal temperatures in El Paso. The gray is the average temperature for the day. The blue is the average high temperature for the day, and the orange is the average low temperature for the day. And so we would expect that on day 61 of this year, we might have a low temperature here of, let's say, 38 degrees. And on day 61 of next year, we would have that same temperature. And so if we consider that this represents 1 year, that would be our period. The length of daylight over the course of a year is also periodic. If we look at this latitude that's in yellow here, any place along that latitude is going to have a dark and light cycle according to this chart over here. So apparently at the month of March, okay, which is also going to be the beginning here, we're going to have 12-hour days. This is going to be on the spring equinox. As we move into the summer solstice, our day length is going to be something more like 14 hours. And in the winter solstice, our daylight would be about 10 hours at that point. This is a picture of a normal EKG that I got off of the internet, and we can use this little marker here to show that this function is pretty periodic. Okay, it's not going to be totally exact because there's always variations from one cycle to the next, but you can see that as I move this around to different places, it does tend to pretty closely correspond one point on a cycle to a corresponding point on the next cycle. And so this is actually what you want your heart to look like, right? Nice and periodic and steady and stable. Even the orbits of the planet are periodic. If we think about periodic functions, let's suppose we have a function f of x that's periodic, and its period is 5, and it's defined by this table. So we could use this table alone to define the function because the distance 0, 1, 2, 3, 4, we have 5 values here, and we know that when we get to 5, we're going to repeat the same values. So we have one complete cycle between this table and this table. So this is going to be f of 0, f of 1, 2, 3, 4. F of 5 is the same as f of 0. And so these are corresponding points on 2 consecutive cycles, and so the period is 5. Go from 0 to 5, 1 to 6, and so forth. What is f of 8? Well, of course, it's 0. Okay. How could we find f of 71 from this information? Well, let's think about it. If we have a table here from 0 to 4, and we know that the table goes from 5 to 9 and repeats the same y values, we can imagine that we would have another table that goes from 10 to 14, 15 to 19, and so forth. And so the first value in each of these tables would be 0, 5, 10, 15, 20, and so forth, multiples of 5. So if we look at 70 here, we know that 70 is a multiple of 5, and that should be another starting point of a cycle in our function. And so f of 71 is going to be 4. It's going to be the same as f of 1. One way to specify a periodic function is to say that f of x, okay, any value of x, is going to be the same as the function value when I take x and add some multiple of the period. So this n is some number of periods. In other words, if x is 0 and I go 1 period, and I know that my period is 5, okay, I'm going to have x is 0, 1 period of 5 gives me f of 5. This is also equal to f of 0 plus 5 periods, okay, which would be f of 5 times 5, or f of 25. And we can continue on and consider that f of 0 would be the same as f of 0 plus 14 times 5, which is f of 0 plus 70, which is f of 70. Okay, so what we're doing here is saying that no matter how many times I repeat, as long as I'm repeating by 5, I'm going to end up with the same y value. So we can use that concept down here to look at some wacky number like 397. Okay, what is actually 1,397, right? So what is the value of the function when x is 1,397? Well, in this case, the pattern is pretty clear. I'm either going to start my table with a last digit of 0 or 5. Here I have 0. And it looks like if I think about this point right here being a last digit of 5, then this should be f of 13, because I'm going in multiples of 5. And so this is 1396, 1397, which is what I'm looking for right here. And so if I just continue the pattern, I'm going to see that f of 1397 is equal to -8. How about f of -347? We might have to think about that a second, but I think the same thing is going to apply. If we go backward then from 0 and subtract 5, we would start our table at -5. And we could start our table at -10, -15, and so forth. And so we could start the table at -350, okay, with again a last digit of 0 here because we're going in 5s, and count upward and find that we should have the same value as the fourth entry in the table. Okay, in other words, f of -347 is going to be 0. How about this number right here? Some gigantic number. We're certainly not going to count by hand all of these cycles, but again, we can see that the last digit here is 6, and because we're going in increments of 5 in this case, we know that this could be all of those numbers ending in 895, all of those numbers ending in 896, which is this, and so we know that the second number in our table is going to be 4, and therefore that number is 4. All right, I want to get you started on this assignment. Question number 1 says that one cycle of a periodic function is graphed below. Plot the points for the next complete cycle, then sketch a smooth curve through the points. So let's look at this first one as an example. Let's determine what the period is. And the period is just the distance between the start and the end of the cycle. So in this case, the period is 5 minus 0, which is going to be 5. So every x value has a y value, and if I take the x value and add the period 5 to it, I'll be at the corresponding point on the next cycle. So from x equals 1, I have a y value that looks like a little less than 3. So if I add the period of 5, I get an x value of 6, and I'm going to plot that same little bit less than 3 y value. Repeat for as many points along the x-axis as you like, and go ahead and connect the dots together. Repeat that for each of these graphs. On the part at the bottom with the tables, this is very similar to what we had in the video previously. And as a matter of fact, this table is very similar because it has the same period. The period is given as 5. So we're going to go 0, 1, 2, 3, 4. Our next cycle will start on 5, 6, 7, 8, and so forth. So use that concept, just like you saw in the example, to determine where would 103 be if I continued and copied this table period after period after period. What about 244? Let's look at this next one. P equals 2. Period is 2. So this is going to be 7, 8, 9, 10, 11, 12, and so on. So you might be able to figure these out pretty easily, but what pattern is really going to help you with figuring out the function value for this number, and especially for something very large like this number? Finally, we have period equal to 7. So we know that our next table is going to start 11, 12. It's going to start here at 13, 14, and go on from there, and use that information to evaluate what would be the function value when x is these two numbers here.